Okay, welcome back everyone. And now we're going to go over tiebreakers when you have redundant links with the same costs to the root bridge. Woo! So let's go over that, right? So tiebreaker for equal cost paths. So if we look at our diagram here, the first connections I'm going to go over are these gig connections here and here. So we know two things. One, that the switch one is the root bridge. So all of its ports are going to be forwarding. Because the root bridge always has all forwarding ports, and there's something called designated, which we're going to get into the rules and states here in the next slide. And then switch 3 has to pick a forwarding or a root port, meaning the one port it's going to forward off to the root bridge. So it has 4 options here. Well, gig 04 and 05 are going to have a cost of 8. So these are not going to be forwarding. And then it has gig 02 and 03, which have the same cost of 4. So to keep it simple, without getting into like the binary, like we did the BPDU, because don't feel it's necessary for CCNA, the tiebreaker is the lowest port number. Essentially saying there is a value that the BPDU and spanning tree places on these actual port numbers. And whichever value is the lowest is the winner. That's going to be in a forwarding state. And now, depending if you're running regular spanning tree or rapid spanning tree, this one would be considered an alternate or just blocking, right? And it just depends on which one you're running, because our STP actually has a state called alternate. STP doesn't, but no matter what, it's an alternate no matter what if this goes down, right? So kind of different flavors. Okay. And now we come down here to 05 and 04. We know that in spanning tree, only one side of this link has to be blocking. So out of these links, which side is going to be blocking? Will it be switch 3s will be blocking, or switch 2s will be in a blocking state? Well, we have the same issue. It's both the same path cost, which really doesn't matter here, but then they're also the same link number. So what's the tiebreaker here? Which one side is going to be forwarding? Which one's going to be blocking? Well, for this, we go back to the MAC address. Which switch has the lower MAC address? And out of these two, the answer is switch 2. So that means these will be in a forwarding state, and switch 3s are going to be blocking. Switch 3s are sad guy here. Almost everything's blocking except that one root port. Okay? So the tiebreaker, when we have equal cost paths, is going to be the lower interface ID. And I want to show you guys something. So I'm going to take a screen capture of this so we still have it. And then I'm going to get rid of this. So I'm going to bring into view a topology here that I kind of spun up. And we have the same topology that we just went over on our whiteboard. So we have ETH01 and ETH10 to switch 1, which is our root bridge. And I want to show you guys what this looks like with a show spanning tree command. Okay, so we haven't gone over this fully yet, but we're in switch 1 here. And let's say we want to see the spanning tree, the spanning tree for switch 1 and VLAN 1. Well, it gives us a lot of information here. The root ID, which is going to be what the root bridge advertises, and it tells us here that we are the root. We see that hello time we talked about and that max age, which is times 10. And then we see the bridge ID. So this is our bridge ID, right? The one we send out. And we also happen to be the root ID as well. You can see we're at the default here of 32,768 with our system extension added, which is VLAN 1. And then you see here when we're the root bridge, we're always forwarding. And since these are Ethernet ports, look at our cost, 100, just like we weren't. So kind of validating what we went over in the actual lecture. And then let's go to switch 3 here, which has the same network design minus the extra switch port here that we have on our whiteboard. Let's take a look which one is forwarding and which one is blocking. And just like in our whiteboard, you can see that each 01, you see this priority number here? It's the lowest out of the other connection 1/0. So it decides to be the root port, that's its role, and its state is forwarding. Pretty cool, right? Kind of validating what we learned. And these switches are running the rapid spanning tree. So in this, we're going to have a alternate, but it's still going to be in that blocking state, okay? So this is kind of validating what we already learned in the whiteboard session. So pretty cool. Now let's go ahead and go back to the lecture portion. Okay, and now we're going to go over the different roles and states. So during the root bridge election, our individual interfaces or connected interfaces between switches are going to go through different states. And then once it goes through the states, it's going to decide on the role of that interface. So let's check out this chart here. So we have the regular spanning tree, and then we have rapid to show you the differences. So in regular spanning tree, start down here, we're going to have a learning and listening state, which is in documentation supposed to be 15 seconds each. Then after these listening and learning states, we're going to go ahead and go into a forwarding or blocking state. And then depending on what kind of state, we're going to decide our roles. And also depending if we're the root bridge or not, right? Because if we are the root bridge, we have nothing but designated ports. But if we have to forward traffic to the root bridge, we're going to have the port role of root port. Okay? And then notice in rapid spanning tree, we just have learning here, which is only supposed to be 2 seconds. And then it immediately transitions you into a what they call discarding or forwarding state. And I like this because it's a little bit more accurate because spanning tree is just discarding any messages that can cause a broadcast storm. Like I've told you, control plane traffic can still come in on our discarding ports because they have those specially reserved MAC addresses that the switch recognizes. And then notice for our rapid spanning tree port rules, we have alternate instead of just non-designated, which means just nothing, right? And then we have designated ports, of course, which are the same, and then root ports, which function the exact same. Awesome. Then let's go over rapid spanning tree real quick and the main differences. Kind of already covered if you just take a look at this chart, right? The main one is that it learns much quicker, the BPDUs. 2 seconds compared to 30 to 50 seconds. And then it has discarding state instead of blocking. So if you're taking like a CCNA test, maybe something you need to know. And then the port role for the blocking states are different. Whereas the rapid spanning tree port role is alternate. And the spanning tree port role for blocking interfaces is just called non-designated. So a little bit more information. The newest flavor is called 802.1 Whiskey. And then rapid spanning tree just improves the speed of STP by only having a learning state for receiving and processing bridge protocol datagram units. And then this last slide, you see it's kind of blank here. I couldn't find a picture, but this is all the flavors of spanning tree that you need to know about. For the test, they just want you to know about rapid, but we have the OG here, which is the IEEE standard of spanning tree, which does not support per VLAN instances. Then we have Cisco's flavor, which is per VLAN, right? We have a spanning tree for each VLAN we have active in our management domain and our switching domain. And then the rapid spanning tree, IEEE standard, 802.1 Whiskey. And then Cisco's per VLAN flavor. And then we have one down here that's not going to be talked about. It's called multiple spanning tree. And this one's great for our large campus networks. And if you stick with us for our CCNP course, I believe we will touch on that. Okay, so our last little chart here that just kind of breaks everything down for you, right? The cost right here that you're generally going to see with 10 gigabit being 2. The BPDU, this is the bridge ID breakdown, with the bridge priority being the default 32,768 in increments of 4,096. The extension ID, which is the VLAN number, then the MAC address. And then we have our STP states and STP roles, and this is just the spanning tree flavor, right? So the only difference here, right, is the rapid spanning tree has alternate, right, for the roles. Okay, so let's just move on from this slide. And now we're going to get into some spanning tree features. So I'm going to go ahead and pause the video real quick, guys. And then we're going to get into this additional features that spanning tree you need to kind of protect your network and what you do for your access ports for interface connections not going to a switch. What can you do to kind of protect them from being flooded with BPDUs or some malicious person trying to make themselves the root bridge? Okay, welcome back, and let's finish up the lecture part of spanning tree. So I just want to show you guys something. I fixed this error on my last slide. I had the states and roles reversed in here. So for you guys downloading the course material, that will be fixed. Okay, and now let's get into spanning tree port fast. So this is another feature that the CCNA exam wants you to know about. So essentially, right, spanning tree is enabled by default on all of our switch ports. So that means if we have an access port here, let's say this is gig 0/9, and we plug in a user computer or endpoint, we're going to send BPDUs to that computer and nothing's going to happen, right? But let's say we have a malicious threat actor here that downloads a Kali Linux box, runs it in a VM, and then tries to, using Kali Linux tools, send a BPDU bridge ID value of 0, the lowest possible, and make himself the root bridge just to kind of cause havoc on your network and maybe a denial of service attack. Or maybe just by doing that, we cause a loop, right? Or a broadcast storm. So what configurations do we have available at the actual access ports to prevent this from happening? We have port fast. And what port fast does is essentially turn off any STP features on that interface and stops any STP election. So no BPDUs are going to be sent. BPDUs are going to be sent. And when you execute this command, you're actually going to see an error saying, hey, you're turning off spanning tree. If you plug a switch in here, we won't be able to detect broadcast storms. And that's okay, because you should only be doing this on access ports. So one of the benefits of spanning tree port fast, other than just the security, is that in your switch network, you don't generate those topology change notifications, which are part of that BPDU packet, which we're going to dive deep into when we do our Wireshark. There's something called TCNs that get sent, topology change notifications in BPDUs, when there's a change, right? Another thing, if you're running the old flavor spanning tree, is that even user ports that plugged in would have to wait that 30 to 50 seconds to then go into a forwarding state, which in today's standards is a no-go, right? Imagine you plug in a user in and you're running the old flavor spanning tree and you don't enable port fast, which disables spanning tree on that user port. They're going to be offline for 30 or 50 seconds before this port decides to go into a forwarding state. Okay? So pretty big deal there, especially if you're running that old flavor spanning tree. And you just don't need spanning tree on if it's just an access port, right? So run port fast. Okay, last feature we're going to go over is root guard. So spanning tree root guard is a feature that allows you to protect your root bridge. Now, what do we mean by this? Essentially, when we enable root guard on a switch and we receive a bridge ID that is better than ours, and we're supposed to be the root bridge, we're just going to send that port to error disabled mode and say, nah, I'm the root bridge in this kingdom. You can't just come in here with your better bridge ID and say you're the root bridge. Now, you may be wondering, like, okay, well, when is this going to happen? If I have complete administrative control over my switch network, when would this happen? Maybe the junior network admin messes up, but kind of a big mess up, almost intentional if they do that. Well, sometimes when we merge companies or we work with a third party or we spin up a business agreement and now we're working with another MSP in our local area, maybe they're running a switch network, campus network that we have to connect to via layer 2, and we still want our separate administrative domains. We can put root guard here. It's going to disable that. Now you may be saying, well, okay, now we've lost connection. Right. But this is just so we don't, this is just in case we haven't done our due diligence yet to figure out the best way to switch our traffic. Okay. And really, this is just a good thing even for malicious users that maybe want to plug in and their own switch to wreak havoc, or they're like a shadow IT is what we call it. User brings in their 8-port switch from home because he wants to plug in multiple computers to be more productive, whatever the case may be. Root guard will send that interface into an error disabled if it receives a superior BPDU. And that's kind of the language you use there. If it receives a superior BPDU, it's going to send that port into an error disabled mode. Okay, awesome. So that about covers everything with spanning tree. If I missed anything, please let me know in the comments. And I hope this information was informative. And thank you guys for viewing. Our next video is going to be going over the spanning tree lab, where we're going to do some Wireshark captures and kind of dig into spanning tree. So thank you.